Welcome back to 2241. And today we're going to do more examples. We've already gone through the overview video. And here we have our first problem. So it says, sketch the graph of the equation z equal x squared in R3. Let me zoom in a little bit. It's a little hard to read. Okay, so we want to sketch the graph of this equation. All right, well, if we're going to do that, we need an x, y, z coordinate space. So here we've got our x, y, and z. Let's move this up a little bit. We need z equal x squared. So maybe we'll move that one as well. So try to make this sort of equal amount in the x, y, and z directions. And we'll label these like usual in standard format, x, y, z. And then we will draw our parabola z equal x squared. And let's draw this as though it's just in 2 dimensions. So we're looking at the zx plane right now. And that's where we're going to draw our parabola. So the positive z-axis is right here, and the x-axis is right here. So for every x value, I get a z value, and my parabola should open sort of like this along that plane, along the x-axis. Let's draw that. I'll use my handy-dandy tool here, parabola drawing tool. This guy looks something like that. Maybe a little bit steeper. Parabola's hard to get right, but it should look something sort of like that. Okay, and then so now we have this parabola, and we're looking for all of the points in R3 that satisfy this equation. Well, points on here look like x, 0, x squared. But I could also have a point x1, x squared. And because the y coordinate does not show up in this equation, this also is a solution. And this is translated, this is that point translated 1 in the y direction. Now I get a point right here. Okay, that's that point. All right, so what I can do is essentially take this shape, not what I wanted to do, sorry. Copy it and paste it right over here. And then, wait, I could also shift the point that I just made a little bit further up to x comma 2 x squared. And then I could shift it down maybe to x comma minus 1 x squared and x comma minus 2 x squared. And hopefully we see where this is going. I can take the same shape and just sort of slide it along the x-axis or the y-axis and get new parts of my shape. Put some more in here, sort of finish this thing off, and then we can draw in the rest of our grid lines here. All right, so this method that I'm using right now is called, this is using traces or sections of the graph. So I've chosen to draw my sections parallel to the xz plane. And now I can put in some other parts of a grid and get a shape that looks a little bit more standardized. I'll try to do this in 3 dimensions as nicely as I possibly can. Not always easy. Do something sort of like this. Okay, and so there's my shape. If I erase, it's going to be hard to erase, but maybe I'll outline it in red. Let's outline it in yellow here. Red, there we go. Okay, so Here's the outline of the shape that I'm interested in. Bottom here. Okay, cool. So there's my shape sketched in 3 dimensions, and I can see all of the traces here and grid lines. And I've understood that this is a parabolic cylinder. So usually we want to classify these as well as sketch them. And this is certainly parabolic, but it's in 3 dimensions, and I've slid along all of the y-axis to get a bunch of parallel lines. That's what these are. These are parallel lines that are perpendicular to the XZ plane, and so this is a parabolic cylinder. Okay, so that's the first problem. Next, we have some more surfaces to sketch, and this time it explicitly asks us to classify them. So we want to sketch each surface and classify it in R3. Let's make another XYZ coordinate space. And since we have 3 equations, I'll make 3 of them. And we will see how they change. So for the first one here, let's give ourselves enough space. Bit of a pun there. Oops, sorry, my pen is dying. But we should have enough to get through the video. So we've got X, Y, and Z. And our first equation is the X squared plus Y squared graph. So X squared plus Y squared equals 1. And in the XY plane, note this one does not involve Z, so I'm going to slide along the Z axis to get the rest of my surface. But in the XY plane, this looks like just a circle. So I'll try to do this nicely. Okay, that's not too bad. Maybe I'll rotate it a little bit. Size and rotate this guy. There we go, that's a little better. Now we have this shape, and we can just copy it up and down the z-axis right here. Copy up and down, and keep going. We should get what looks like a circular cylinder. This is the standard shape that we usually call a cylinder, and we'll draw the rest of our grid lines here in the orthogonal direction. It looks like it didn't make all of these perfectly parallel. Maybe want to move this over a little bit. Here. All right, and then we have a few more back here for the grid lines. Okay, so this is more or less the process you want to go through when drawing these. And then just to help yourself out, you can draw the outline of your shape in different color maybe, once you're done with that. And then over here, we will do the same thing with the next equation, y squared and z squared equal 1. And so this time we're looking at things in the YZ plane, and so our circle should look like this. We'll draw our circle here. All right. And again, we'll just copy paste this along. 1, 2, put some more in. And you really don't have to do a ton of these, just enough to get the shape of the graph. So that's probably plenty. And now I can draw in the rest of my grid lines. 1, 2, 3. Oop, not what I wanted, sorry. 3, 4, 5. Hard. Zoom in here and, oof, boy. Let me get these grid lines right here. Then we can move on a little bit. There we go. Okay, so good enough. And now we can do our outline. And that's our y squared plus z squared equal 1 equation. All right, and then so you can probably guess what this one's going to look like. This one is a vertical cylinder. This one is an in and out cylinder. So the cylinder is going to go along the y-axis. I guess I'll have to move my coordinates over a little bit here, make some space. All right, and at this point, I know what this is going to look like more or less, and I just go ahead and draw my shape directly in there. That should be pretty good. Copy, paste, and move it over. Now, if you're doing this by hand, you'll have to redraw the circles, of course. But the idea is the same. Just copy that shape over, left, right, up, down, in, out, wherever it needs to go. Go. All right, rest of our grid lines now. Oops. Go. And then we can fill in our shape, or the outline of our shape. And it should look something like this. All right, so there's our set of 3 cylinders on the XYZ space. All right, next up it says use traces, explicitly use the traces to sketch the graph of this function. Now I always use traces, I just think it makes things a lot easier to do, especially when you need to draw things in an actual coordinate space where the size of things matters. Let's go ahead and try to do this here. So more so we are just getting used to what these equations end up looking like in 3D space. Okay, and then we need our labels, X, Y, Z, and we have x squared plus y squared over 4 plus z squared over 9 equals 1. Okay, so this looks like the equation of a circle, except it has an extra term, the z squared term, so maybe a sphere, except now we also have these coefficients that scale the size of those radii a little bit. And so if you remember, for an ellipse, when you draw something like, make something up here, I don't know, x squared over 4 plus y squared over 16 equals 1. So if this is the equation of an ellipse, this 4 right here is 2 squared, and the 16 is 4 squared. And so the radii of the ellipse, this is 2, and this is 4. That's what those mean. And I kind of drew this in the wrong order. So this would be the x-axis, and this would be the y-axis. It's called the minor axis and the major axis is what these are, the minor radius, major radius. Okay, and so in 3 dimensions, we have more or less the same idea. We can identify those radii. We've got a radius of 1 squared, 2 squared, and 3 squared along the x, y, and z axes individually. And so if we draw those in here, let's say x has a radius like that, y has a radius like this, and z has a radius that's much longer. So that last one that I drew Be a little smaller. A stroke eraser. So that needs to be a little bit smaller than this. Maybe more like that. Okay, and then we can draw in our ellipse. I'll try to do this one by hand. It can be sort of a pain in the butt to do it with the tool. But the ellipse should more or less look something like this. And like that. Here we go. And then in the XY plane, it looks something like this. That last one needs to go a little bit smoother. Very convenient that I can easily erase and redo them. And then the last bit looks more like this. And sort of like that. There we go. And so there is our ellipse in 3 dimensions. And here maybe I can make the back part look a little better. So we can sort of understand the structure of the ellipse better. It's going to look something like that. Sorry, the ellipsoid a little bit better. All right, and there we go. So we have our ellipsoid. We just have to recognize the equation here. It's got plus, 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 x squared plus y squared plus z squared all equal 1. If it's not equal to 1, just divide that over. And then whatever you have down here, the square root of it is the radius. So this was radius 1, this was radius 2, and this was radius 3. And that gives us our ellipsoid. All right, problem 4. Use traces to sketch this one. Oh, I didn't write down this as an ellipsoid, so we might as well do that. Ellipsoid. Keep forgetting to classify these. Oh, and we didn't classify these as well, did we? So these are circular cylinders. They're elliptical cylinders, but ellipses that are circles. All right, so let's finish off problem 4 here. So we need our, again, XYZ space. Drawing in general. A little more space here to draw this, which is good. Oh, and I actually want this a little bit further down. And I might make the axes non-standard in this case. So let's make this the positive x-axis, that the positive y, and this the positive z. I guess you could also make this the positive y-axis, but then the ellipse would be very, very non-standard because it would be, or sorry, the coordinate system would be very non-standard because then it would be inverted. Remember, your right-hand rule says you need to have x, then y, then z, and then back to x. If I put y over here, then I have x, y over there, and then z going in the opposite direction. Okay, so now we can draw in our thing here, and let's try something a little bit new. What happens if I take this equation and I set y equal to 0? Well, I get what the trace of the equation is in the xz plane, or zx plane. We get z equal 4x squared. Okay, so what happens if x equals 0? Well, then I get z equal y squared. And this is just our standard parabola now, just in different planes. Okay, and then what happens if I set z equal to maybe 1? Well, then I get 1 equal 4x squared plus y squared. And if I rewrite this a little bit, I get 1 equals x squared over 1/2 squared plus y squared over 1 squared. And now I can see my radii, the xy directions. So my radius in the x direction is a little bit smaller than the radius in the y direction. Right. So yeah, all right. So we can take our parabola drawing tool here and make our, maybe we'll make our y part first. So we have a standard parabola there. Again, parabolas can be sort of a pain to draw, but we'll get it. Good enough, okay. So that's our y parabola. And then the x parabola should be a little bit steeper than that because it has radius 1/2 right there, or it's got a 4x right there. So this turns into something a little bit more like that. Make it sort of steep. And then on the other side as well, we have a parabola. Something sort of like this. Okay. And so now I can draw in my other grid lines. These were ellipses, as you can see right here. And I'll draw them by hand. Make this a little bit nicer looking, maybe. And really, these parts are the only ones I can see. So the other ones will get dotted lines. Sort of like that. There we go. Okay, so there's our elliptic paraboloid in XYZ space. All right. Oh, I guess I can fill in the rest of these grid lines as well. Something sort of like this. Does look a little bit messy, busy if you put too much in, but generally you want to kind of get the idea of what the coordinates look like. All right, and then here we have our last one with fewer instructions. I keep forgetting to classify this. This is an elliptic paraboloid. All right. And then down here, we have z equal x squared minus y squared. All right, sort of the same format as this one, except we have the minus now, and you can probably guess that this is going to be a hyperbolic paraboloid. We'll go ahead and draw it out just to be sure, but that minus should tip us off right there. All right, so we'll put in our coordinates, yellow, go, just like this. And note that we have the same coefficient on x as on y, except for one's positive, one's minus. So we should have the same size parabola in each direction. So we can label these with our usual standard coordinate system. No reason to change anything there. And we'll draw our parabola. Okay, so notice that the x parabola opens upward and the y parabola opens downward. If y equals 0, we get z equal x squared. And if x equals 0, we get z equal minus y squared. And that minus tips us off that it's a downward parabola. So we can draw our minus parabola here. And our positive parabola in the other direction. Here we go. Positive parabola looking something like that. And that's more or less what this thing should look like. Okay, and then we sort of want to connect the dots here. So this will be a little bit trickier, but what you can do, and this is sort of a neat trick, is you can say, all right, well, what does this thing look like if I look at lines, look at what it traces as on lines through the origin. So lines through the origin are satisfied by y equal let's say alpha for the slope x. Then if that's the case, we have z equal x squared minus alpha x squared, and we get 1 minus alpha squared times x squared, and this just becomes a parameter that allows us to decide what kind of parabola z we have along the z-axis when we are looking at a specific line through the origin. Okay, so if we're looking at the line with slope, let's say -1, alpha equals -1, then we're looking at this line that I've been drawing, and we get z equal 1 minus -1 squared. And yep, that is exactly what you think. We get z equals 0. So we get a straight line through the origin that is on the graph, actually. Put that in red. Straight line through the origin, literally on the graph of this function. And then, all right, well, similarly, if I set alpha equal to +1, then I get 0 as well. So there's another line that's on the graph of this function. Turns out there are infinitely many lines that just have different slopes, but that's one way that you can get this. And those lines will not be through the origin in every case. Right? What about for, let's say, alpha equal to 2? Or let's say -1/2. That's a better one. So if alpha equals -1/2, then we get z, I guess plus minus, z equal 1 minus plus minus 3/4. Jumping ahead of us. Squared x squared, and this ends up being 3/4 x squared. So a little bit smaller than the standard parabola, or shorter, but still going upward. So our graph ends up looking a little bit more like that in those two directions. Like that. And then maybe you can start to connect the dots a little here. What's going on? Well, as I draw my shape, I start twisting this alpha line along the xy plane here. I'll draw out more and more of these parabolas. And well, this, and this all have to be on the graph. And this thing should sort of change continuously. So I should draw my graphs going through the end points of these lines. All right, let's see what that looks like. if I start here, draw a line, something like this, and then my graph is going to become come back down that way towards that part of the paraboloid, and then back up, and then it's going to have to come up through the red line there, and then back up through the blue line there, back down. It's got to hit that one that's on the graph, and then that red line is on the graph. It's going to come back down here to that blue line, which is going to go right back up, and then back up here to that blue line. And now in white, you can see your saddle shape with your two standard parabola along the x and y directions there. It's a little busy, so I'll get rid of those again. All right, and that's our hyperbolic paraboloid. Bit of a weird looking shape, a little harder to understand. Okay, so that is the first half of our examples. This is a bit of a longer video, so I'll break it up into two pieces.